Hey all. So here we're going to start on a thing called Cramer's rule, which is actually a really neat little tool. Um, it doesn't get a lot of attention, sadly, because it is a really actually pretty useful thing. This comes in extremely handy when we're trying to solve an equation like ax equals b, where we really only care about one of the values of x. So not one of the, sorry, one of the coordinates of x. So in the case that I've got like a system of equations and I've got like current and voltage and resistance and like a whole bunch of other stuff about a circuit, right? Maybe I really only care about the voltage at one point. This gives me a quick way to get a hold of one of the values without having to like row reduce the entire system. It's not great for solving equations like this generally. Usually, row reduction is going to be a more efficient process for this. But if you just need one of the answers, or you need in pure math, we oftentimes have this way of just being like, okay, look, I just need an answer. Cramer's rule gives me a convenient way to write down a form for my answer. So what we're looking at is we're looking at an equation like ax equals b, and here I've got a matrix A, a vector x, a vector b, right? And then what I'm going to do is I'm going to make some new stuff. So I'm going to make a new matrix. I'm going to just say, let's define, I'm going to define this matrix x1. This is capital X1, is going to be our vector x1, x2, yada yada here. And then I'm going to fill this in with the rest of the identity matrix. So this is essentially identity except I subbed out a row. Right, so I'm going to have zeros all the way across this top row. I'm going to have more zeros all the way across this guy. I'm going to have a 1 here. I'm going to have ones all the way down the diagonal. All of this crap's going to be 0. All of this crap's going to be 0. Everybody on board with this guy? All right, so the neat thing about this x1 vector is I can know one thing about it. I can know that the determinant of this x1 matrix, sorry, I just called this a vector. This is a matrix. The determinant of this matrix is actually just the value little x1. I could notice that by row reducing, right? If I use this first row to row reduce, I'm going to get rid of all of the xi's except for that first one. That's going to be my pivot there, right? So I'd get little x1 out of this. That's convenient for me. Another thing I can notice is if I take my matrix A and multiply it by x1, right? I'm going to get A done to each column, right? So I'm going to have A done to the vector x in my first column, and then I'm going to have, well, if I do A to this vector here, I'm just going to get the second column of A. So this is going to be A1, 2, A2, 2, on down to A N2 here at the bottom. If I do that again, right, my third column, I'm just going to get the third entry. So I'm going to have A1, 3, A2, 3, and so on. So down to AN3. I'm going to kind of continue that, right, all along here. And eventually here at the end, I'm going to get ANN in the bottom corner and A1N up top here. So this matrix, right, is just like, well, it's like A, but with the first column substituted out. Well, what's AX, though? AX is supposed to be B, right? So this is going to be a new matrix here. I'm going to dump my little thought bubbles because I actually want to think about this one. I'm going to get a vector B here, right? And then I'm going to get all of the guts of A, right? So actually, let's make our lives a little easier here. Let's just go ahead and delete this guy. We'll take our matrix A over here. And really all I need to do is wipe out that first column. So we're just going to go, whoop, first column's gone. And in here is the vector B. Right, so when I do A to X1, I just get A, but with the first column subbed out for B. So I'm going to call this matrix B1. And then I'm going to notice something. I'm going to notice that I know a rule about determinants. I know that the determinant of a product, so A times x1, is the determinant of A times the determinant of x1, which is little x1. And that this is actually equal to the determinant of this new matrix B1. What that does is that lets me write down a formula for x1. X1 is the determinant of the matrix B1 divided by the determinant of the matrix A. So that gives me Cramer's rule. And Cramer's rule is just relatively straightforward. Cramer's rule says xi is the determinant of the matrix bi divided by the determinant of the matrix A, where bi is A, but with the ith column replaced with B. And that's pretty cool. So let's do a quick example. Should be relatively straightforward. So here's my example. I want to solve this little matrix equation. So I've got 3, 4, 5, 6 times xy is equal to 2, 4. And so I'm going to say, all right, so x then is going to be the determinant of the matrix 2, 4, 4, 6. So that's, I took the first column out of my matrix A here, right? So I'm thinking AX equals B. And this is B1, right? I replace the first column of A with B. And then I'm going to divide by the determinant of my little matrix. Oops. 3, 4, 5, 6. You can hear the dog is very concerned about determinants of matrices. So here on the top, I've got 12 minus 16 over 18 minus 20. So that got me negative 4 over negative 2 gives me 2. And y is the determinant of my little matrix here. I'm going to leave the first column alone now, so that's 3, 5. I'm going to put 2, 4 here. Oops, I needed a closing matrix bracket. And then I'm going to divide, and I actually already know what the determinant of A is. That's negative 2, so I'm just going to put a negative 2 down there. And here I'm going to get 12 minus 10 divided by negative 2. So I got 2 over negative 2. So I got negative 1 out of this. So let me double check that, right? So if I take 3, 4, 5, 6 and multiply by 2, negative 1, what do I get? I get 6 minus 4 is in fact 2, and 10 minus 6 is in fact 4. Check. This worked out. That's cool. So Cramer's rule is an interesting little thing. You're probably not going to see it a ton unless you end up doing one of the engineerings that has lots of solving differential equations. For some reason, this gets a lot of airtime in those kind of engineering solving TEs. So if you end up in electrical engineering, for instance, you're going to see Cramer's rule a ton. If you end up in pure math, you'll see it occasionally. If you end up in one of the other engineering fields that doesn't deal with a lot of linear algebra, you may not see this again. But it's a cool little trick, and it's a neat way to solve something relatively quickly. Thanks for listening. Catch you guys on the next